Okay, last week, these slides are from last week. Last week, we started out BlueSpec by showing this example of a greatest common divisor implementation. We pointed out that in a module, because in BlueSpec, everything is a module. And this is pretty much, at least that single statement is pretty much the same across most hardware description languages. Everything is a module, starting from the top level module. So everything is a module. Inside each module, we have state. It could be registers, 32-bit registers, 32-bit registers, and 32-bit FIFOs. And FIFOs are fixed size. By default, they are of size 2. And besides states, we have behavior, which is rules in BlueSpec. They have guards. Guards could be implicit or explicit. Explicit guards are described this way after the name of the rule. All of these Boolean statements need to be satisfied before this rule can actually be scheduled to execute. They can also have implicit guards, where if the rule calls methods of other modules, for example, outQ here is a FIFO, which is a module. It can try to call outQ.inQ, but inQ may have its own set of implicit or explicit guards. And if this outside rule, if step 2 wants to call outQ.inQ, outQ.inQ's guards, all of them have to be satisfied. Otherwise, this whole rule won't fire because all of these rules are transactions and they're atomic. So they're transactions being everything needs to execute or nothing will. So if we ever fall, if the conditions under which this rule is executing is such that y minus x equals 0 is satisfied, and we have to go into this if statement, but the inQ output that outQ.inQ's guards, some of them are not met, then this whole rule will never fire because this is a transaction. So that's rules. And we also talked about methods. Methods are just like class methods in C++ or Java. And methods also have guards. It could be explicit, like the if statement you see here. One interesting thing here is that for methods, the rules, the guards, explicit guards have to have an if statement at the beginning, but for rules that they don't. This is just a syntax issue. And of course, methods can also have implicit guards. For example, this action value method result needs to call output outQ.dq, but outQ.dq has either implicit or explicit guards such that if output q is empty, then the guards are false. So if output q is, the q is empty, then it is not allowed to actually call .dq. So if output q is empty, when someone wants to call result, then this whole method is uncallable. So if there's an outside rule which wants to call this result function at any point, and output q is empty, then that rule cannot fire. That rule as a whole cannot fire because that rule is also transactions, is a transaction. So I mentioned that it looks, from a high level, it might be easier to understand if each of these rules, you think of them as threads, which are just forever spinning until all of the set of guards are met, and then it executes everything in a transaction, and then it returns to spinning, so that it can execute it again and again and again forever whenever the guards are met. So that's a kind of a natural abstraction to think about rules. And because you can have thousands, hundreds of thousands, millions of, maybe not millions, but thousands of rules in your design, each of these rules can be thought, can do some amount of parallel work, which is where a lot of the parallelism for FPGAs come in. So this is the example BlueSpec code, which I hope is kind of useful in presenting the basic language details. And before we actually go to using this language as description tools, I just want to go over a little bit semi-formally the relevant functionalities of the language. So we're going to talk, again, this is pretty much the same stuff we talked about in the past couple of minutes. We're going to talk about modules, rules, and what's in them, state, and then a little bit about functions. So I'm going to power through them as quickly as I can so that we can move on to the actual hardware design stuff. So right, BlueSpec modules. Modules also have interfaces. That's a pretty hefty statement to start out with. Anyways, modules in BlueSpec and in most other hardware description languages as well they encapsulate state and behavior. So register, transfer, RT, state and behavior. And they're kind of analogous to classes in C++ and Java. And when the outside world meaning pretty much outside methods or outside rules, want to access the internals of this module, much like you would need class methods to access the internals of a class, it needs to access it through an interface. So the interface definition is separate from the module implementation, and many module definitions can share the same interface definition, so which results in interchangeable implementations, hopefully. So if a module requires a FIFO and uses a FIFO interface for something, then if you have different implementations of FIFOs with different size, different behaviors, different scheduling or something, whatever you can think of, different internal implementation, it could be using block RAM, it could be using off-chip DRAM, it could be using remote memory or something like that, it could be anything. If the interface is the same, then you can just swap it out fairly easily. So this probably sounds a little bit like virtual classes in C++. I'm pretty sure Java also has similar provisions as well. And you would be right. Interfaces act very similarly to virtual classes in C++, such that all it does is that it defines or enforces a set of methods and method signatures so that you can implement different things and then have it swapped in and out without too much trouble. Interfaces can also be parameterized like C++ templates, but that's not too important right now. So an example would be easy way to get into this. Remember, this is the same module we were talking about a couple of slides ago, module make GCD for greatest common divisor. And if you remember, I haven't pointed this out when we were talking about this, but the code actually says it uses pretty much like you can almost say it inherits a interface called GCD IFC. And you have to have an interface definition for GCD IFC somewhere, typically inside the same file, that defines the methods that the module should implement. So GCD IFC defines the action method, start. Action being if it is able to make state changes. The method is able to make state changes. Or it also defines a method, action value method, which is action value method result. Action value meaning it can make state changes, and it also returns a value of bit 32. So if make GCD uses the GCD IFC interface, pretty much like a class inheriting a different class, a virtual class, for example, it has to implement the same set of methods. It has to implement start with bit 32A, bit 32B as arguments, just like we did in GCD IFC. But the internal implementation can be whatever you want, whatever this module wants. It can have different implicit, explicit guards. It can have whichever internal operations that you want it to do. Results is the same, action value returning bit 32 result. And internally, this module can decide what to do with it. So yeah, you can have a module called make GCD, which implements this GCD IFC. You can have another implementation of make GCD. It could be make GCD2 or whatever, which also inherits this GCD IFC. And each of these modules can be used interchangeably. Much like, we'll see examples of this pretty soon. And we kind of pointed this out already. Inside each module, you can have interface methods. So I kind of briefly mentioned action and action value methods. Action methods can take input, modify state. For example, it can set new values into registers. That's That's kind of modifying state. It can enqueue or dequeue from and to FIFOs. Action value but action methods don't return anything. Action value methods return something. It can return something, and then it also modifies state. It can also modify state. It doesn't have to. So action value methods kind of encompass is the superclass of everything else. So which kind of begs the question, why don't we just have action value methods? The compiler can actually figure this out internally, but it's just a language feature, I guess. You can also have a value method, which returns a value, but cannot modify state. We'll show examples of this pretty soon. Methods can also have guards. It can, like we talked about here, this one has a guard, an explicit guard. And this one has an implicit guard, which we talked about already. And of course, it does not allow execution. The rule that wants to call this method cannot fire at all. The whole thing cannot fire unless the guard of this method is true. And yeah, this fairly straightforward, the kind of stuff you expect. If you have an action method, which does changes state, but not returns anything, you can call it like this. If you have a value method that doesn't change state, but returns something, you can use it like this. If you have an action value method that does make changes into the state, but also returns something, you can use it like this. Note that it has a kind of a strange notation for using the return value. There's a long and strange history about why this particular arrow is used in this place, but right now it's not important to us. It's only you have to use this arrow for action value methods. That's pretty much it. BlueSpec modules also support polymorphism, which means modules can be parameterized with types. For example, before when we talked about, when I showed GCD-IFC, that was it. There was a semicolon here and that was it. But it can also be parameterized with a type or a numeric value or something like that. So in this example, instead of building a GCD implementation for a 32-bit bit type, maybe I can define a GCD-IFC to take whichever type that the user wants. It could the user can give it 64 bits, because user can give it 23 bits, whichever. And since we are parameterizing val type, I can actually write the start method to use a val type for A, val type for B, and then val type for result. I can do it this way. And inside the actual implementation of the module, which implements GCD-IFC, this parameterized GCD-IFC, I can also use the val type label to refer to the type that we're dealing with. And there's a lot of complexities that involved in actually implementing parameterization or polymorphism, but we're not going to talk about this here because it's not necessary for the purpose of lab 2 at least. So yeah, the only thing that I guess we need to take away from this slide is that, for example, when we instantiate a register or FIFO, which we saw before, it uses a very similar syntax: register parameterized with bit 32. Just like how if I had implemented GCD-IFC in this way, GCD-IFC can be parameterized with bit 32. So this is basically the mechanism that the register interface and the MICREG implementation is using to get input from the programmer for how many bits, for example, needs to be stored in this register 1. So that's basically it. This is an example of polymorphism, which is used to give parameters to these modules. Slightly less important topic, I actually considered leaving this out, but just in case, it shows up in lab 2. BlueSpec modules can also take module arguments. Modules can take other modules and variables as arguments. For example, when we do GCD-IFC, it can actually take other modules as input. The type arguments, the interface arguments, the polymorphism stuff went here, if you remember from the previous slide, after the IFC. But module parameters go here in the implementation side of things. And it can take modules, integers, variables, numeric values, et cetera, in this position, depending on how you implement your module. And these arguments are available inside the module context. So for example, if you give a register, a name of a register, 32-bit register, for example, 32-bit register called A, and you give A as an argument here. Inside make GCD, you can use A just as if you had instantiated a local register. So that's possible to do, especially if you have, for example, a very complex module. If you have a memory controller, for example, which has lots of interface methods, and you don't want to wire them together one by one, you can simply give the memory interface, the BlueSpec interface, as a parameter to the module, and you can use it internally just like you would outside. And that's an easy thing to do. But typically, if it's at all possible, this is not typically recommended because when you put something like argument reg, which in this example, this is a register of bit 32. If you give this to a module, it is still a single implementation. It is still a single instance somewhere on the chip, a physical instance on the chip. And if this register, and when you use it in the context of module arguments, it's very easy to just give this one register to a bunch of different modules, bunch of different module instances. And if you do that too many times, all users, meaning all of these hosting modules, must be located nearby on the chip physically to satisfy the timing constraints of accessing this register. So if a lot of modules, if 200 modules all take this one register as a parameter, then all of these things, these 200 modules plus this argument reg, needs to be located close enough on the chip to have a single cycle communication between them. And sometimes that can be detrimental. So typically something like this is not highly recommended. So if copies can be made or updated via latency and sensitive signals, etc., that's likely a better solution. Yeah, that's just a high-level overview of modules. And just like any other language, if you get into details, there's a lot of caveats, there's a lot of features, there's a lot of cool stuff in this language as well. But of course, there's, just like any other language, there's a learning curve to become very proficient at it. And at least for the purpose of the labs we want to do in this course, this kind of high-level introduction is, I hope, enough. So that was modules. The second important thing in BlueSpec is rules, because rules are what defines behavior. Behavior, the transfer part of RTL, the sequence, the combinational circuit part of the circuits. This is where the actual computation is done. So rules in BlueSpec are atomic actions on state, which are only executed when all the guards are met. We talked about this multiple times already. Explicit guards can be specified by the programmer, like such here on the bottom. Implicit guards, meaning all conditions, meaning all guards, be it explicit or implicit, all conditions of all called methods should also be met. So, and then again, this is rules are not only atomic, they're also transactional, meaning everything that that needs to execute at once, or nothing will execute, or this rule won't fire at all. For example, take this rule as an example. There's rule step 1. It has a bunch of explicit guards. It does some work on the registers. It swaps the values, actually. And if x equals 0, for example, it runs some action method. But let's say when this, in the context in which this rule is firing at a particular point in time, the explicit guards are met, x equals 0, and action value methods guard is not met. So if you're thinking from the point of view of a software language, for example, a step-by-step kind of a software language, you might easily think, oh, this rule will start firing because the implicit guard is met, explicit guard is met. It's going to do the stop work. We go to this if statement, and because x equals 0, we're going to start executing this thing. But because the guard of the action method here is not met, we're going to be stuck here for a while after we already swapped X and Y. That's not what happens with HDLs, because most of the times it is completely transactional, meaning when the rule starts firing, it does all the checks for everything before we do any sort of actual state changes. So if the explicit guard is met and X equals 0, and then the language actually checks if the action methods guards are all met before we do anything, before we swap X and Y, for example. So even if the explicit guard is met, if X equals 0 and the action methods guards are not met, the X equals Y swap doesn't happen at all. Nothing in the rule fires if that's not met. But on the other hand, if the explicit guard is met, X equals not 0, and if we don't go into this if statement, then it doesn't matter if the action method here, its guards are met or not. So yeah. So in that case, the swapping will happen even if the action method its guards are not met, because due to this if statement, we didn't need it. We didn't need to execute this at all. So basically, this is a transaction. It's just that in software implementations of transactions, most of the time what happens is that you try executing something, and if you run into an exception, you roll everything back. Instead, in the hardware description language example, transactions are implemented such that all the conditions for everything is checked beforehand before we actually start doing any work, so that only when we can execute everything that we need to, because of the if statements, because of the guards, et cetera, after we check everything, only after we check everything to check if all the guards are met, we start executing anything at all. So right, yeah, if a method call is inside an if statement, the method conditions only need to be met if the condition is met. Yeah, and this example represents an implicit guard. The rule doesn't fire if both of these guards are not met. If X equals not 0, then it doesn't matter if the action methods guards are not met, etc. Yeah. Another side effect, rather, or actually the fundamental characteristics of BlueSpec rules being atomic transactions, is that each statement in the rule only has access to state values from before the rule started firing. So we talked about this in the previous lecture already. Let's see what, yeah. And this means because each of these rules don't the state changes that each of these statements, each statement being each of these lines or each of these, each of these lines, each of these statements only have access to the state values from before the rule started firing. There is no dependency between any of these statements. So all of these rules, each line of a rule in BlueSpec, you can think of it as separate parallel operations. So each statement executes independently, and state updates happen all at once as the result of the rule firing finishing. So what does that mean? It means is that, let's see, if we implement X equals Y, set X to the value of Y, and set Y to the value of X. If we implemented these two lines in a software language, you would have executed this line and then this line. So if X equals 0 at the beginning of time and Y equals 1 at the beginning of time, after this line executes in a software language, after this statement executes, X will be 1 and Y is still 1. And after this line, Y would be 1 and X will still be 1. So at the end of the execution in a software language, you would have gotten X equals 1 and Y equals 1. But in an HDL, because these two lines execute in parallel separately, even though one of them happens earlier in the code than the other, both of these lines are executed at the same time in parallel. So the Y in this context is 1, represents the value of 1. X in this context is not affected at all by the results of this line. X in this context only looks at the value of x before the rule started firing. So x here is still 0. So as the result of this line, x equals 1 because y is 1. As a result of this line, y equals 0 instead of 1. Y equals 0 because in the context of this statement, x is 0. So x equals 1, y equals 0. An interesting caveat of this is that because each of these rules are independent, if there are two statements that try to update the register value, update a state, and update the same state, for example, if you have two lines here, two statements, one of them wants to set x to 1, one of them wants to set x to y. If this was a software language, x equals 1 will turn x into 1, and then x equals y will turn x into, well, 1 again, because y is 1. But in an HDL, because these two statements are independent and in parallel, x will equal to 1. These statements want to execute together at the same time, but they all want to update the same register with potentially different values. And when that happens, semantically, it doesn't make sense. We can't know which is the correct value to actually end x with. So this results in a write conflict error complained about by the compiler. And yeah, we talked about this already. The exact same example as the previous line. If there's an if statement and a implicit or explicit guard inside, all of them have to be, if the if statement is met, the guards of the output q.enqueue also needs to be met. If the if statement is not met, the guard of the output q.enqueue doesn't matter. Everything executes or nothing executes. That's atomic transactions. Another interesting thing, which is actually becomes important when you're actually doing design with these languages, is that rule execution is kind of clock synchronous. At a high level, a BlueSpec rule feels very similarly to the always block you would see in Verilog if you have experience with Verilog. It's just has a little bit more functionality, including things like guards and scheduling. Yeah, so just like the always blocks in Verilog, rule execution is clock synchronous. Meaning, in a simplified explanation, a rule starts execution at a clock edge. It could be a rising clock edge or a falling clock edge. But typically, if you don't do anything special, it's a rising clock edge. So a rule starts execution at a clock edge, and it must finish execution before the next clock cycle goes up. And this is just the inherent characteristics of doing hardware design on silicon, pretty much. If it's clock synchronous, each transaction, each operation, could be an always block or a rule or whatever, needs to finish its operation within this clock cycle, because at the next clock cycle, it needs to do something else. So if a rule is too complex, if it has too many, say, multipliers inside a single rule in a critical path, or if it has very complex conditionals, so if you have a lot of stuff in the guard, too many stuff in the guards, then it might not fit inside a single clock cycle. And if that happens, the synthesis tool, typically vendor-specific tool, could be from Xilinx, could be from Intel, it could be an open source tool like Yosis. It can perform static analysis of timing of each of these rules, always blocks, whatever, and then it will emit an error saying the timing is not met. And if you actually try to program this onto hardware, then you might get unexpected results. You can choose to ignore this. You can just program this onto the hardware and see what happens, because sometimes the programmer can know better. Like even if this particular path does not meet timing, we can have reasonable margins or safety regarding being actually safe. But normally, if you run into a timing error, it will probably produce unstable or just straight up wrong results. So yeah, getting all the rules fitting inside your given clock cycle speed is one of the important optimization points in hardware. So when this happens, the programmer can either break the rule into smaller rules, multiple smaller rules. It could be pipeline, it could be something else. or you can modify the clock speed to be faster or lower. So for example, if you have a clock that looks like this and you have two rules, rule 1, firing at every given cycle, but rule 1 is simple so that before the cycle actually finishes, it can finish whatever it was doing. But rule 2 could be too complex so that when at the rising clock edge, rule 2 starts doing stuff. It starts addition, multiplication, whatever. But the critical path of the resultant circuit is too long, so that it spills over into the next clock cycle. If this happens, this represents a timing error. And because rule 2, for example, rule 2 might want to start firing again at this cycle, or the results or rule 1 might be wanting to read the results of rule 2, which still not be in a stable state. It could just still have garbage noise in the circuit, because it hasn't settled down to the value that it really actually wants to produce. So if you have timing errors, we're probably going to get wrong results, that's something we want to avoid. So that's rules. We're going to talk a little bit more about timing in the near future, because that's an important part of hardware design. It's an important optimization point of hardware design. And so we talked about modules, we talked about rules, and next is BlueSpec state. State is just registers, FIFOs, and other things that store state across clock boundaries. If you write something to a state element, to a register, or whatever, other rules or the writing rule even itself can read the value that it wrote at the next or further later clock cycle. State is typically expressed as modules with their own interfaces. The most prominent state element is registers, one of the most fundamental modules in BlueSpec. And the details are not important for us right now, as you just use it like this. It's a register of type something, bit 32, for example, and then you instantiate it using make register, giving it an initial value. When the chip is fired on, chip is powered on, which value will it start with? You can give it 0 or 1 or whatever. You can give it a question mark. If you don't care what it starts out with, you can give it a question mark. And note that here's this strange arrow syntax again, single arrow syntax, like when you ran an action value method. There's a history and caveats to why this syntax is chosen, but for now, it's simply good enough to remember this strange single arrow notation is used only in 2 places, when you call an action value method and when you instantiate a module, 2 places. This is different from when you assign a value to a register, when you use a double arrow notation. Yeah. Anyways, so that's registers, which is typically just like regular variables in software. There are many caveats there, but it's an easy enough abstraction to have. And registers, which are state, is not to be confused with things that are not state. For example, you can give temporary variable names, temporary labels to values within a rule. For example, if you have a register A, which is of type 32, this is a state. And inside a rule A, we can create a temporary variable of type bit 32. Note the missing reg here. You can't have you can't have module instantiations within a rule. So we're creating a temporary variable of bit 32, which represent the value of register A plus register A. And this temporary variable dA is defined only within rule A. And of course, this value is ephemeral. It's not maintained across rule executions. It is not maintained across clock cycles. So the value that's stored in dA disappears once the execution of rule A is done. This value is not accessible by any other rules or by rule A after the execution of this one rule. So it's very ephemeral, just like a local variable within the context of this single basic block. Yeah, so this is simply a temporary label given to the value reg A plus reg A. reg A plus reg A. So yeah, I just wanted to point out this is not state. It actually doesn't exist on the chip anywhere except as this is just a label, a temporary name. The temporary name the language the compiler gives to a bundle of wires, which is a temporary manifestation of the computation. Anyways. Yeah, temporary variables are not actual state realized within the circuit. There's no flip-flop, there's no register that actually holds that value. It is just a name and a label tied to another name or combination of names. It can be written outside of rule boundaries. There's a natural scope ordering rule that apply when that happens, closest first. Similarly, if you have if statements or for loops inside the rule, the natural scoping rules do apply. And in this case, instead of using the double arrow notation when you write to a register, you can use the regular equals assignment to assign each value to a label. So you can do something like this. Boolean BFQ is something. And you can actually use the value of so there is dependency relationships across these code lines for these temporary label assignments. So for example, if BFQ had been a register and we had used double arrow notations to assign a value to BFQ, if we try to, we're going to mention this a couple of slides down, but this is this display statement is telling the BlueSim simulator, when you want to simulate the circuit, to print this line onto the screen. This is pretty much like a printf. If BFQ had been a register, and we gave BFQ as a parameter to the printf statement, then this would have printed out the value from the previous clock cycle, because all of these statements have access to registers values from before the rule started firing. But because this is a temporary variable, when you do this, it actually prints the value of the result of this statement. So there is dependency for temporary variables. There's no dependency for registers. So it's a subtle difference. And this is a characteristic that almost the same syntax, the same relationships exist for Verilog as well. So this is pretty much a widespread HDL thing. So that was registers. Another prominent state element for BlueSpec is FIFOs. FIFOs are one of the most important modules in BlueSpec because the BlueSpec language kind of nudges you towards not using less registers and more FIFOs, so that all of your design can be kind of microservice-ish design where they're all passing messages between each other. In my experience, it does really help with implementation. When you use a default implementation of FIFOs, it has a size of 2 slots. And you can, of course, use different variation implementations with various characteristics. And this acts very similar to a queue that you would expect, like, for example, std queue, std list, or whatever in software, except for the fact that it has a fixed size number of slots. And a default FIFO implementation exposes 3 methods: enqueue, dequeue, and first. Enqueue is an action method. It blocks when it's full. Dequeue is an action method. It blocks when it's empty. First is a value method. It blocks when it's empty. So expectable stuff, expected stuff. And when there's a rule that wants to call any of these functions, and one of the guards are not satisfied, that wants to enqueue something, but the queue is full, for example, it raises an implicit guard so that the whole rule does not fire. FIFOs are provided as a library, so you need this line at the top to actually use this. Yeah, so you can use it. We showed this. I showed the example code for using FIFOs multiple times already. So this is a typical way using FIFOs is a typical way of implementing pipelining in BlueSpec. Instead of using pipeline registers, pipeline flip-flops, typically you would implement a pipeline with FIFOs between each pipeline stages. each rule doing some amount of work. For example, if we apply it to the 5-stage pipeline in a RISC processor, a decode stage, for example, could do the decode work, and the decode results are pushed into a FIFO, and the execute stage will DQ and get the head value from the intermediate FIFO to continue doing the work in a pipeline banner. And because these two are connected using a FIFO, both the rules that each implement the decode and the execute logic can always be firing at the same time in a parallel way. I hope this makes sense. Otherwise, I'm going to show examples for hardware design guidelines using BlueSpec as well. So hopefully, when we come to that part, all of this is going to become a little more straightforward. I missed the questions from before. Let's see. So running the conditions first, assignment later. Yes, as long as it meets the syntax, it would make absolute sense to write your conditions first and assignments later. That's a fine way of doing things. Yeah, unless the rules become too complex, then depends on. I mean, this is just a code clarity issue, like you said. It depends on how you want to do it. There is a way to make statements execute sequentially. You can implement a finite state machine in BlueSpec, etc. Typically, it's done by just creating a rule for each statement that you want to execute sequentially. So if you want to execute A, B, and C in order, you need to create a rule A, B, and C, each of which that do something, set a value to a register, read a value from that register, and so on. But if there's too much of that, then it could represent low performance because you're doing things sequentially instead of in parallel. Anyways, various types of FIFOs are provided by BlueSpec. For us, it's not too important right now because things like FIFO F instead of FIFO, the interface is different, FIFO F. FIFO Fs have two additional methods, Boolean not empty and Boolean not full, which are never blocked. You can create mixed size FIFOs with giving a integer value for how many slots you want to have in the FIFO for FIFOs of larger sizes. You can have mixed size BRAM FIFO, which implements the FIFO using block RAM, the larger size block RAM. So you can have FIFOs of size thousands of slots if that's something that you require. And many more. There's a bunch of stuff, but you probably don't need to talk about all of this for the purpose of this class. So hopefully all of this will become clear, self-explanatory when we start actually looking at the actual code. There's also a concept of wires, which you can use if you want to transfer data between rules within the same clock cycle. But I don't think this is necessary for us right now. So we're going to, in the interest of time, I'm going to skip ahead. Right, and inside the rules, this is probably just straightforward stuff, and stuff you would expect from any kind of language. So I'm just going to move very quickly here. You can have write, this special write statement with a $sign in front of it. You can give a debug message. You can format it like printf. It prints to screen. It acts very much like printf. It only works when compiled for simulation, for functional simulation using bsym. But if you actually compile it for hardware to get the bit file you want to program to the actual chip, all of these statements that start with a $sign are ignored. But you can put that in a rule if you want to have debug statements. And most of the stuff that you would expect from normal languages are there. You can have if, else, if, then, else, and end, although the syntax kind of looks strange. If, begin, end, else, if, begin, end, else, begin, end. You can also have arithmetic operations. There's the usual addition, subtraction, multiplication, division, and a couple more, XOR, stuff like that. There's also logical operations that returns a Boolean value for comparing the size, checking equals, nots, logical and ors, all that stuff that you would expect. Also bit operations. Say we have a 4-bit value A and a 4-bit value B, so 4-bit, 4-bit. We can concatenate this into an 8-bit value using the curly braces notations to concatenate into an 8-bit value. We can concatenate the, truncate the 8-bit value to a 4-bit value. We can truncate the lowest bits of the 8-bit value to a 4-bit value. We can extend it by padding it with 0 from a 4-bit value to an 8-bit value. You can, if you have a signed type, you can also do signed extend, but this is not important for us right now. And you can also use the regular substring notation to get, say, 2 bits from the 4-bit value. So that's that. Moving forward, we talked about the equals assignment for temporary values, the double arrows assignment for writing to registers. No need to go any deeper. I'm going to jump forward. BlueSpec also has functions, which are typically defined either within a module or outside the module. Functions do not allow state changes, partially because it can be defined outside the module as well, so state changes won't make sense there. So it only encapsulates some computation on a set of input parameters and then returns a value. For example, we can have a function called square, which takes a integer 32 parameter, integer 32 return. Integer here is signed integers, and it returns a value multiplied by value. And this function called square can be used within other rules. So this is just one way to encapsulate a lot of commonly used computation. BlueSpec types. BlueSpec is a strongly typed language, very, very strongly typed language. It has many basic types, bit, int, unsigned int, etc., etc. Strongly typed meaning if we have a bit 32 of A, B, and then bit 16, smaller one, of C, and I try to do A equals B plus C, BlueSpec doesn't automatically extend or truncate these values for you. It just, this line, because B is a 32-bit integer, 32-bit bits array, and C is a 16-bit bit array, this operation fails during compile time with a type mismatch error. So you need to either do 0 extend to C so that C turns into a 32-bit integer. How many bits it needs to extend it to is automatically determined by the compiler. Or you can do truncate C into 16 bits to work within the same 16-bit space. BlueSpec also supports many compound types, including tuples, vectors, maybes, and unions, etc. But we won't go into all of that. I'm just going to quickly point out a couple, because I really want to get to the hardware design guidelines before the end of this lecture. It can have tuple types. There's a bunch of them, tuple 2, tuple 3, all the way up to tuple 8. So these are types. Instead of typing something like bit 32, you can type tuple 2 of different types. When you are setting, maybe let's just look at this example. So we can create a FIFO, you see on the bottom here, which instead of holding multiple slots of bit 32s, for example, these scalar values, we can have tuples. This FIFO named TQ, where each slot is a tuple of 3 values, and each of the tuple slots are bit 32, Boolean, and int32. So you can use it like this. And when you enqueue into this FIFO, you need to be able to define a value, a tuple 3 value. In that case, you use a syntax like this, tuple 3, but you give it the first slot with the first index, which is a bit 32, you can give it this value. The second slot Boolean, you can give it false. For the last slot int, you can give it this value. So with this line, you're pushing a 3 tuple value into the FIFO TQ, where each of the values inside the 3 tuple is this, this, and this. And when you actually want to read the sub values of a tuple, you can get the tuple 3 value from the FIFO by calling tq.first. And then you can access the first, second, and third sub-values by saying TPL_1, TPL_2, so on and so on. So if there's a tuple 2 of x and y, calling TPL_1 on this thing will return x. For a tuple 3, x, y, and z, for calling TPL_2 would return the second slot, which is y. Very straightforward things. I just have to, at least mention it once so no one gets too confused. There's also a compound type vector, which is parametered by the size of the vector and then the type of each slot. There's a bunch of different ways to access this as well, but again, just looking at examples would probably be easier. You need to import vector to use it. It was the same with tuples as well. So I can create a register, if the first line, I can create a register. And in this register, I can have a vector. The single register will store 8 vector of int 32s. And I can call migreg, and the default value would be just a new vector with undefined values. Or I can give it, I can use this replicate function to fill all of these 8 slots in the vector with 1s. Or I can even do a 2-dimensional vector, a single register holding a 2-dimension on one side, 8-dimension, let's say x dimensions of 2, y dimensions of 8, each of these 2 slots holding bit 32. And in this register, I can use replicate of 0 to fill all the slots with 0. I mean, this is one way I can do this. And I can use it with regular vector notations, regular array notations you've seen in most other languages. I can do all this stuff, 2-dimension, 1-dimension, so on and so on. An interesting caveat of implementing vectors and registers in a hardware language is there's 2 different ways of implementing a state element of vectors. One option is I can create a register of vectors, a single register with a single write signal, for example, which has a vector type. So it would look like this, a register of vector 32 with 32-bit values. And I can set all the values inside this one register with 0. A second option is using a vector of registers instead of register of vectors. So in this case, instead of creating a register first, I create a vector first. So this R file name, variable name, now represents 32 registers, each with 32-bit values. So here, instead of doing replicate inside the makereg module, I can do replicate M, which is pretty much replicate modules. It actually stands for something else, but there's a lot of caveats there. So right now, let's just say this is replicate modules. Replicate M of makereg 0. So this is one register, but I'm just replicating it 32 times. And each of these approaches have different and disadvantages, advantages and disadvantages. And typically, the difference is that comes in when we are doing partial writes. So if I do register of bit 8 R, and then I do sub-bit assignment. So because R here is a single register, even if I want to write to a single bit, if I do R bracket 0, I'm just writing the lowest significant bit right. I'm setting that value to 0. Because this whole 8 bits is one register, when this operation is actually executed, what the hardware will do is read the entirety of the 8 bits and then update one value and then write the whole register back. So yeah, something like this is happening. I'm reading the whole register R into R new. I'm setting the single bit of R new to 0 and then writing the whole thing back. Basically, this is how the actual hardware will be implemented. So if I do something like this, if I create a register of vectors, so all these 8 value slots, all sitting inside one register, if I do, even if this is a vector type, not just one bit 8. This is a vector type. If I do something like this, it counts it as a read and write to the entire register R. So if I want to have two separate rules, for example, or even inside one rule, where one statement writes to the sub slot 0 and the other statement writes to sub slot 1, this counts as two writes to register R, which results in a write conflict error. On the other hand, if I create a vector of registers, then R is 8 different registers in hardware. So R0, writing something to R0 is only a write to register R0, so this does not cause a write conflict error. But then again, having separate registers instead of having everything inside in a single register also does have some circuit overhead. So some small amount of overhead per register. So which one to use depends on your use case scenario. I think we're almost done. We can also do, in order to reduce the complexity of your code, we can have the compiler do automatic type deduction using a statement called let, kind of like auto in C++. So the let statement enables users to declare a variable without providing the exact type. So instead of, so say x is an int32 type. So when I do x plus 1 and assign it to somewhere, I don't have to explicitly write int32 value equals x plus 1. I can do let, and the compiler will automatically deduct that value is int32. But because the type of value has been deducted at this line and it's int32, if I try to compare, say, if I want to add value, which has been deducted to be int32, to value 2, which is explicitly set to int16, if I try to do something like this, the compiler type system, the BlueSpec type system pretty much gives a compile time error saying int32 and int16 doesn't match. Yeah, these are all statically typed because pretty much they're hardware. Okay, so that's it. That was the lightning round into BlueSpec functions, at least I think all we need for us to do lab 2. So armed with that knowledge, if you look at this line again, it should all make sense, hopefully. There's a lot more topics we can go into if we want to become experts in BlueSpec, but that's not the purpose of this course. So there's a lot more topics, including complex types, type classes, polymorphism, rule scheduling, static elaboration. There's a lot of really strong, powerful capabilities of the language that lets you have very high productivity when you do hardware design. And I think in my research group, the productivity of this language is one of the big strong points of this R group compared to some other groups. But that's not the purpose of this course. So I'm going to stop here with the language. And we can finally get to the part that I'm very excited about, which is FPGA accelerated design principles. And basically how to, kind of like what we did with CPU-based topics and GPU-based topics. We talked about architecture, we talked about the programming model. Now we're going to go a little bit into how do we write effective software/hardware for these platforms. And this topic for FPGAs comes in two parts: designing pipelines and timing issues. And compared to, and I think personally, the theories involved in optimizing for CPUs, caches and AVX and all that stuff, were relatively straightforward and simple, so to speak. I think in retrospect, the theories and principles involved with GPUs was a little bit more complex and involved, because we talked about warps, we talked about the shared memory banks and things like that. So it was a little bit closer to the architecture and a little bit more complex. And unfortunately, with FPGAs, when we want to actually take benefit of the architecture, the optimizations involved here is actually also even a little bit more complex. So just putting it out there before we start. Yes. So when we design a system, when we want to design a system for high performance, there are typically two different potentially orthogonal things that designers typically care about. One is achieving high clock speed. So designing hardware for low delay, meaning each rule being simpler most of the time. So designing hardware for more delay, which results in higher clock speed, and also designing hardware for higher throughput per clock. So these two potentially, sometimes they're intermingled, but many times they're not, many times they're orthogonal. So typically designers aim to create a design with a very high clock speed, as well as per clock, we want to do as much work as useful work as possible. There's a lot of techniques involved, including how to do good pipelining, getting wider data paths, widths, latency and duty cycle issues, and implementing computations as filters, things like that. But I hope we can point over at least a couple of these things. So when we design stuff for FPGAs, it's maybe important to point out a little bit how the fundamental shape of the computation structures may be slightly different. So back to Flynn's taxonomy of describing parallelism, we talked about SISD, single instruction, single data. This is pretty much just a single core processor looking at a bunch of instructions, looking at data. Or even in a multi-core processor, if each of the threads are doing completely separate work for separate purposes, each program would be doing SISD kind of work, single thread pretty much. Or we can, so far we've looked at a lot of SIMD stuff as well, single instruction multi-data, where a single instruction represents pretty much the same work being done on multiple different instances of data, SIMD. So SIMD extensions like AVX and GPU stuff fell into this category. Or there's also MIMD, multi-instruction, multi-data, where it's a multi-threaded implementation or even distributed system, which have kind of a shared nothing architecture where each thread is doing their own thing. On the other hand, FPGAs, of course, this isn't always an ironclad rule, but typically, when we're starting out, an efficient way to do FPGA design is to target MISD, multi-instruction single data, which is an important subclass of this is something like a systolic array, which we will get into in a bit. So this is pretty much a pipeline from a high level what we're looking at. We have a data stream that moves through different processing units, and each of these processing units do different pieces of work to finally produce the actual result that we want. And to implement this efficiently, it is, again, there's a lot of asterisks being put into all the statements that I say, because none of these are, FPGA design is a very free process. I mean, there's a wide array of doing efficient design in different ways. So I'm not trying to say this is the way to do things. This is just a good way to get into FPGA design at the beginning and try to kind of get efficient results. But a good way to start is trying to implement computation as so-called filters. Filters are computation units that looks at a small window in a data stream and emits a different stream. So if you have an input stream, you push it into a filter, you stream it into a filter. The filter is not looking at the whole, at most points, it is not holding the entire data set in its memory at any point in time. It only looks at a small moving window of the input stream. So when the input data moves out of the stream, it gets thrown away, and it takes a new input instance from the input stream, and so on and so on. And the filter emits a different stream on which the filter has done some form of computation on. And this is a colloquial definition. A lot of books or different people define it slightly differently, but I think this is a pretty okay way of describing things. And architecturally, a filter can be implemented using a MISD type systolic array. And this is good for FPGA type designs, and we'll get into the differences in a bit in the very next slide, actually. Because it only looks at a very small window, there's a very small memory requirement. And which means even if the input output data is large, there's no need to store it in its entirety anywhere. And everything is processed in a streaming manner. so that most of the times each of these pipeline stages don't have to have a holistic view of the entire data set. It only has to do its part of a very small piece of work. Of course, yeah, it reduces on memory requirement because on-chip block RAM resources are precious. And if you can avoid having to go to off-chip memory, then we can save a lot of performance. So this filter-based, moving window-based implementations are typically very efficient when you're trying to do something on an FPGA. And this, well, yeah, I'll talk about the why architecturally FPGAs work very well with this kind of approach after a while. So let's look at an example. There's a construct called the FIR filter, finite impulse response filter. It is, quote unquote, discrete signal processing filter whose response to a signal is of finite length. So the simple intuition is that when you have a stream of data coming in, imagine a sensor or something on an IoT device or something like that. And at any given time, after certain intervals, it gives some piece of data. And maybe I should have put an application example here first. That could have helped, I guess. But anyways, so a simple intuition, let's just go to the formal definition. A simple intuition is that a stream of data goes into a filter. It does the data stream, meaning the entirety of the data isn't being copied onto the filter at the same time. Data, as it's generated one by one, is being fed into the filter. And the output of the filter is, again, is a stream, one output element after another. It's not being emitted at the same time. So each output of the filter is a weighted sum of n most recent input values. So let's say X is the stream that's coming in. So X0 comes in, X1 comes in, X2 comes in, X3 comes in, so on and so on and so on. So at time point n, the results, the output of the filter will be looping over I equals 0 to n, large N. So Xn is the current type step, Xn minus I, so Xn minus 1, Xn minus 2, Xn minus 3, so on and so on, up until large N. We're going to multiply it against the weight for each I location, and then we're adding everything together. That's it, very simple filter. And depending on the weights that we can give for each of these I slots, we can use it to implement many filters, including low pass, band pass, high pass. For example, I've seen a FIR filter implementation of a heartbeat delineator, so that it chops up each heartbeat signals into heartbeats. Yeah, weights are calculated using discrete Fourier transforms, etc. But for our purposes right now, this is not important. Our purpose is implementing this thing in hardware for FPGAs. And if you were to implement this thing using a naive non-filter solution, would be to store all inputs, all of X, in an array in memory, and then loop over it. So if you implement this in software style, you would probably have a 2-layer for loop. The top level loop I will be looping over this entire input array. And for each of these slots, each location of I, we will have a different for loop, sub for loop, which loops over the window. So we will have 2 for loops where the inner for loop is looping over this red box. And at the next loop iteration, it will loop over this box, it will loop over this box, so on and so on. So we will have a 2-layer for loop, and yeah, and for every first level loop, so for each of these red boxes, we will either store or emit one result of the filter. And because we have 2 two level for loops. And at each of the innermost for loop iteration, we'll be looking at a single slot in this red box. We only need one ALU because we're doing at most one, we're processing at most one data element per cycle. So we use one ALU. If this is a CPU style sequential programming approach, one operation per cycle. And depending on your workload, this might be fine. However, this solution is still very inefficient in hardware. First, it needs a memory to store the entirety of the array, either using precious on-chip memory or expensive off-chip memory. And second, only one element is processed each cycle. So if the input is of size n, and each of these red boxes are of size m, we need n multiplied by m cycles to actually get the entirety of the results. Yeah, because one's kind of in the order of one cycle per one inner loop iteration, meaning n cycles per output. If the window size is n cycles per output. So it would be better if we can break the array into parallel portions. We can break the array into portion 1, portion 2, portion 3, and assign it to different multiple processing units, and that's fine. But it does also add circuit space for overhead for managing computation state of each processing elements, because we need to make sure everything is done so we can stitch them together, etc. But anyways, it's a much simpler way to implement this using a systolic array-ish filter type approach. And the hardware for that will look a little bit like this. We have an input statement, we have an input stream, and we have 4 different units, 4 different multiplier units. Say if you're looking at a filter window of size 4, for example. We can have 4 different units, and these are all pipeline registers or pipeline FIFOs, so that in the first cycle, element moves here, the next cycle element moves here, the next cycle element moves here, the next cycle element moves here. So once all of these registers are filled, at any given cycle, these 4 multipliers all have work to do. This multiplier multiplies this value against this bias, this weight. This multiplier multiplies this value against this weight. This multiplier multiplies this value against this weight, so on and so on. So for window size of n, we are instantiating n multipliers. For window size of 4, we're instantiating 4 multipliers. And once all the multiplications are done, we can also parallelize the addition process by first having a dedicated multiplier for adding these 2 things together, and then have a dedicated multiplier for adding these 2 things together. And then, because now there's 2 elements, we can have another dedicated multiplier for adding these 2 values together. So there's 3 adders operating in parallel. So as long as this pipeline is completely filled, every cycle we are doing n multiplications and then log of n adders. So here we're doing 4 multiplications and 3 adders per cycle. So for n of 4, we're doing 7 ops per cycle, as opposed to 1 ops per cycle from the previous approach. So basically, we're using a pipeline tree of adders coupled with n multipliers and doing computation of doing something like this. We have a stream of stuff coming in. We have a multiplier for each slot in the window that we're looking at, and the adders are all parallelized as well. So in this approach, as soon as after the initial 4 cycles in which the pipelines is completely filled up, we are always doing 4 ops per cycle. And if the window size is larger, we're doing many, many more operations per cycle, as opposed to the 1 operation per cycle approach that we were looking at before. And there's really no need for any sort of memory, because the data is coming in as a stream. We only have to keep track of the window size, elements in the window, and the output can be emitted immediately. So this is a very efficient way of implementing something like this, and also represents kind of paradigm shift from what you are probably used to in with software. And this is something like this is probably what we will need to do for Lab 2 as well. Although for the purpose of Lab 2, I'll provide a very, very gently guided approach to actually pulling it off. So in BlueSpec, the code looks a little bit like this, the exact same thing that we were looking at before. We're going to use FIFOs and vectors, so we import them. There's an interface called FirFilter IFC. It has an InQ, DQ, and first. Each element is going to be of bit 32. So InQ is where the X's come in. DQ and first is where the results come out. And here, we're going to just assume the window size is 2. So we're setting a complex stuff, but we're setting a type of filter window to be 2. Because we need, yeah, anyways. Yeah, and the we're defining the weights that we're going to multiply everything together with using a vector of filter window, bit 32. And each of these weights are set to a certain value statically. And we have internal FIFOs for internal FIFOs, pipeline FIFOs, and also the result FIFOs that we're going to use to push the data to adders, and then the output FIFO. Straightforward. And of course, we can simply implement the interface method as such. The InQ simply pushes the data into the internal queue, the first internal queue, because the internal queue is a vector of queues. The output DQ and first simply takes the DQ, uses the DQ and first methods of the output queue. Now our work is simply to take the first internal queue value and do the actual computation. And even the actual computation is fairly simple, because we only have window of 2 slots. We can have 2 rules for calculating the weights. For the first slot, we simply we get the first value from the internal queue, multiply it, and then push it into the next internal queue. And for the next slot, we simply take the internal queue 1's value, multiplied to the weight, and push it into the add Q1. In the previous rule, we pushed into the add Q0. And we have an adder rule, which simply takes the values from the 2 add queues and then adds them together and pushes it into the output queue. And this BlueSpec code is simply implementing the FirFilter for a window size of 2. And this is pretty much the approach I think would be sufficient with Lab 2. But a side question that we're over time. Let me just quickly wrap up this slide. A question that you might have with this kind of code is, what happens if n becomes very large? If n becomes 128, do we have to replicate this code n times? And one of the big strengths of BlueSpec is that it allows programmatic, let's say, replication of code. This is what's called static elaboration. We can create a for loop for creating multiple instances of the rule, the for loop looping over integer I, and we have, can use this I to parameterize all of our code, so that writing this one for loop will be sufficient in implementing all of the multiplier rules. Using this method to implement the adder tree is slightly more complicated because it's a logarithmic thing, so I don't show it here. This is an example of static elaboration in BlueSpec, and I don't mean to focus on this too much here because I don't think this is an advanced feature that we don't necessarily need for the purpose of the labs. So yes, so that's it. We went slightly over time, but we finally managed to get into the hardware design guidelines. I guess we can continue doing this to the next lecture. And then after that, we're going to start looking into neural network accelerators, which aren't necessarily in FPGAs, and we're going to talk about ASIC implementations as we move to the, I guess, the apex of efficient silicon usage. We started from CPUs, GPUs, FPGAs, and now we go to ASICs. That's pretty much the best we can do with given that we are working off of silicon. And once we kind of get the feel of neural network accelerator architecture, that's when the lab 2 is going to come in. Okay, cool. Yeah, the pipeline systolic array-based approach is one of the two, I think, at least personally, one of the two pillars of efficient hardware design for FPGAs, for ASICs, or whatever. Once we go on into neural network architectures, you will see that commercial accelerators such as the TensorFlow processing unit in Google stuff are all operating on pretty much the same principle as the ones you see here, and that's an interesting thing to look at. The second large pillar is managing timing, which is kind of annoying, but it's an important piece of digital design. So we're going to talk a little bit more about pipelining and handling latency in the next lecture, and then talk a little bit about timing issues in the next, hopefully in the same lecture as well. Great, thank you very much. That's the end of today's lecture. If you have any questions, I will stick around. Hope no one's running into too much troubles with Lab 1, I guess.